Hello, my name is Rob Reynolds. Welcome to section 311, Calculus. Today we're going to talk about related rates. And we're looking first and foremost at a circular patch. So I know I might need the equation of a circle, which is pi r squared. I might need the circumference, but you'll see I'm looking for area here, so I'm choosing pi r squared. And another keyword is at the rate. Well, there's a keyword, the radius of the oil patch increases at a rate of 30 meters per hour. So remember, the rate of change is the slope, and the slope is the derivative. So I think they just gave us dr, the derivative of the rate at which the radius is increasing with respect not to x, but to time. So dr dt is 30. And what we're looking for is how fast is the area increasing, given that this is the rate that the radius is increasing. And then they say at a specific when the radius is 100 meters out. So we'll plug this in at the end. We'll ignore that. We'll write this in general form. So they're asking us to find the rate at which the area is increasing. So we're looking for the change in area. That's the derivative of the area. So let's take the derivative. If this is area, the derivative of the area with respect to time is pi times 2r times dr dt. And the reason that I need dr dt is because it's the derivative of the radius with respect to time. So let's plug in a couple things. We've got 2 pi. Now they gave us at the radius. I told you this is at the end, so we didn't want to plug that in earlier because then that would just be a constant and we'd get a 0. And fortunately for us, they gave us that the rate of the radius was changing at 30 meters per second. So I think with all this information, we can punch this in and get around 6,000 pi, which if they ask for a decimal equivalent, that's somewhere around 18,850 meters squared because it's area per hour. So the strategy for related rates is, I would suggest, is always write down what's given and then write down what we're trying to find. And in this case, this was given. And by the way, the radius was given that we didn't plug into the end. But this is what we're trying to find. Oh, and you got to come up with some kind of an equation. So here's the author's explanation. It looks like he got the same answer, which is always good. And so here's the book suggestions about how to solve related rates problems and their steps. But I would always try to just list what's given and what are we trying to find. And of course, we need an equation that we're looking for. So the last time the equation was just of a circle. This time I see a triangle. So I know all sorts of, as soon as you say a triangle, I know the area of a triangle is 1/2 base times height. I know relationships of sides. I know SOHCAHTOA. I know the Pythagorean theorem. I know x squared plus y squared equals c squared, the hypotenuse squared. I know all sorts of things about a triangle. I could come up with others, but those are some main ones. The problem to find out what's given. Two small planes are approaching. So here's an airplane and he's approaching this direction. And if the airport's kind of like on an X and Y axis, I would almost wonder if this is a negative direction that he's flying. So when he's flying due west along the X axis, that's dx dt with that's the derivative, that's the rate at which he's flying along the x-axis. I wonder if you'll let me write that as a negative 120, even though it doesn't appear as a negative 120 in the problem. I wonder if I can convince you that since he's flying in that direction, that you'll let me put negative 120 miles per hour. Because remember, velocity is different than speed. Velocity, I have to worry about the direction. So this guy is flying due north, so I think that's dy dt, but since he's flying in a positive direction up, I think I would just keep that 150 miles per hour. This was miles per hour. So assuming that they fly at the same constant elevation, here comes what we're trying to find. How fast is the distance between the planes changing? All right. The distance between the planes is represented by this hypotenuse, because as the planes, move closer and closer, then that's decreasing. So the distance is decreasing at a certain rate. So they've defined this as z. You could do c, but let's just use their variables. So they're asking us to find the rate at which that hypotenuse labeled z is changing. So we're looking for dz dt. And it looks like a couple other things were given. Westbound, it's 180. I'll probably plug that in maybe a little bit later. So x is 180, where northbound, it's the y-axis going up and down. Northbound is 225. Those are distances, which are always absolute values. So don't worry about the positive and the negative of those, because distance is always positive. But they didn't give me z. So if this is 225 and if this is 180, I can quickly find z by doing a squared plus b squared equals z squared, and solve for z, which I think turns out to be about 288. You can do the Pythagorean theorem as well as I can. And then I think I'm going to write the equation just in general terms. So don't use the 225 and the 180. Let's just go back to maybe this equation, and to find, this is now a z. So to find dz dt, I think I'm going to take the derivative of this thing. So the derivative of 2x is 2x dx dt, plus the derivative of y is 2y times dy dt, and the derivative of z, well, you guessed it, 2z dz dt. So the only time I don't have to write the dx dt, dy dt, or dz dt is if I would have taken the derivative of time. Then it would have been dt dt, which is just 1, and then that just cancels out. And nobody ever writes that. But every time you run across a variable that's not time, then we need to worry about the chain rule or the u du lesson. So let's see if we can plug a couple things in. We got 2 times the x value given, 180, the rate, negative 120, plus 2 times the y value, 225, times its rate, 150, is equal to, fortunately we solved for z, so 2 times the 288, and we're looking to take this thing and actually solve this for dz dt. But divide both sides by 2 times the quantity 288, 2 times the quantity 288, a bunch of 2's can cancel, at least, and maybe more can cancel, but you just multiply this together. I would probably just grab my calculator at this point in time. My pen stopped working, so sorry. 150. So now we're down to number crunching. Crunch that thing and go find dz dt, and I think it turns out to be close to negative 192 miles per hour. And if we didn't have the negative, then it wouldn't tell the whole story. I like the negative because, remember, the rate is decreasing. So that negative tells me that it's a decreasing rate. So I kind of like that it turned out to be negative. That makes sense to me because they're getting closer and closer together. And the next couple of slides you can read through. I posted this, of course, on Blackboard, but good. That's always a good sign. The author got the same answer, but he might have had a different way to explain it that resonates with you. So feel free to read through the author's notes as well. Example 3 gives you the volume of this cone, which you may not have memorized. So again, I might give you some things. And here's a relationship. The radius is 3 times the height. And reading this real carefully, it says, how fast is the height changing? So I think we're trying to find dH dt. Given this volume function, so if the volume is 1/3 pi r squared h, then I have a couple of variables, and I think I can get rid of one of the variables by a quick little substitution because it's defined for me. The radius is 3h, so I wonder if I could clean this up a little bit and just say 3h, then everything is in terms of h. So 1/3 pi times, let's see, that's 9h squared times h. So I finally get down to the volume is really equal to 3 pi h squared. Cleans it up a little bit. So if that's the volume, then taking the derivative, I would have dv dt is equal to, let's see, this is not a 2, apologize, this is a 3, because h squared times h. And so 3 times 3 is 9 pi h squared, and then remember your dh dt for the chain rule. And I'm looking if they've given us dv dt. So I didn't read everything up. There it is. The sand is falling in the bin at a rate of 120. So that's the rate at which the volume is filling up. So I believe they gave us this volume, 120. Is equal to 9 pi, let's see if they gave me h, and of course we're trying to find dh dt. Oh good, they gave me that the height of the pile, they gave me h is 10. So I'll plug that in here, and I'll solve for dH dt. So once again, I would grab my calculator, take 120, divide by the 9, divide by the pi, divide by 100, and get dH dt equal to around 0.042 feet per minute. Let's see if the author has something close. That looks familiar. Yay, I think that's what we had. Worked a triangle problem, and this might look like another triangle problem, but I think we have to use a little bit of trig to solve this one, or SOHCAHTOA. So I think I do want to solve or spend a little bit more time talking about this, but we might also use this a squared plus b squared equals c squared business as well to solve for lengths of sides. So we might have to use a bunch of things. So let's read again. And the first thing I see is there's a little guy here, and he must be 200 feet. So that's an x distance away from some site. And it looks like we're trying to find the rate at which this angle is changing. So the angle of elevation is increasing. We're trying to find, that's d theta dt, the rate at which this angle is changing. And the vertical height is hidden just a little bit, but it looks like it's vertically rising for 30 seconds at a rate of 4 meters per second. And if you multiply that together, 4 times 30, it looks like the vertical height here would be about, well, so they almost gave this to me, not quite, but it looks like the y would be a height of 120. So I think I am going to use this real quick. If this is 120 and this is 200, I could do the a squared plus b squared equals c squared to solve for this side. Well, maybe I don't need that side because they didn't ask for that side. They asked for d theta. And usually when I use theta, I'm not using a squared plus b squared equals c squared. I'm using relationships of sides, which means use SOHCAHTOA. So let's look. They're giving me the opposite and the adjacent, and that trig function is the tangent. The tangent of theta is some y distance over x. Now, you may ask, well, why didn't I throw in this 120 for y again yet? And I'm going to leave that because that's until the very end, after I take the derivative, because that's what's changing. This 200, he's constant. He's not walking forward or back. This 200 is a constant, and I can just let that be a constant. But this y, don't you agree that the balloon is rising? And so that's what's affecting the change in the rate. So I'm going to leave that 120 out for when I find the derivative, which I will do now. So let's take the derivative of both sides, and because I need to get to d theta dt, and I think I'll create it right here. The derivative of tangent, if you remember, is secant squared theta, but then we remember the du. D theta dt is the derivative of the left side. The derivative of the right side, well, the constant just pops out, 120. The derivative of y is y prime, which you could write as y prime, but remember that's the same thing as dy dt. Unfortunately for us, they gave us that, so I should put that up in here in the given, that dy dt is 4. They told me the rate at which this balloon was rising. So right here is going to go 4 divided by the 200. I'm also going to divide by the secant and bring that down here. Secant squared theta, just to get my d theta dt all by itself. But remember, instead of dividing by secant, that's the same thing as multiplying by cosine. Like I might end up with cosine squared over 50 for d theta dt. So let's take a moment and explore what the cosine squared, well, let's just look at cosine first, and then we'll square it. So the cosine is defined as what? Adjacent. Uh-oh, look at that. I do need to find this guy right here, because this is my hypotenuse. So go ahead and finish this up. A squared plus b squared equals c squared. I think this is close to 233.24 after I do the Pythagorean theorem. The adjacent sides right here is the 200. And I hope you know how to solve for theta then. You do the cosine inverse of 20 over 233.24 to get theta all by itself. Remember, once you find theta, we still have to square the thing. So I think theta turns out to be around 0.86. If you can't get that, email me, and I'll show you how to get that on your calculator. Second cosine of that. So I want to do 0.86. Remember, you have to square it and divide by 4 and to get d theta dt, which I think is somewhere around 0.015 radians per second. Don't feel, oh, good. Yeah, 0.86. This all looks really familiar. Hey, good, good, good. There's the author. So I'm going to end this video just because of the length of time, but I can tell you on every calculus test, there's always a ladder problem. And this ladder is like sliding down the wall, and it's, of course, the footing is going off. So they're actually giving you dy dt, and they might say that it's slipping against the wall. So this problem will be on your test. The ladder problem will be on your test. And I think there it is, number 23. Can you just work through this? And if you can't figure it out, you definitely want to ask me before the test. I'm just going to be straightforward. This will be on your test. It's pretty straightforward. You do, it's worked out here for you, but before you look at that page, I would just try it. I think you're going to be doing x and y, so I think you're going to be doing this x squared plus y squared equals 13 squared. And remember, when you take the derivative of this side, you just get a 0. So you should be okay, but if not, shoot me an email. You need to know this. If you have questions, be sure to ask. Thank you.